So, welcome back to our video lectures on projective geometry. Last time I gave you some formulas that relate the Beltrami Klein model and the Poincare Disk model of the hyperbolic plane, and this time I want to give you a 3D picture that shows you how to get from one model to the other one. So we ended our last lecture with this picture here, which is again taken from Felix Klein's book on lectures on non-Euclidean geometry, and this picture here explains how the two models are related, and the purpose of the entire lecture today is to get a kind of vivid picture of what's going on here really. So let me first give you an explanation with that picture. So you take your Beltrami Klein disk and you take a line in the Beltrami Klein disk, and then you project it orthogonally up to a unit sphere sitting exactly on top of that disk, and your line here becomes a circular arc. Actually, it becomes a half circle here in the lower hemisphere of your unit sphere. And now you take this circular arc here and project it down to the plane again, but this time stereographically from a projection point that's sitting in the north pole of the picture. And what you get is, well, the lower hemisphere here will be projected into a bigger circular region down here, and this half circle here will be projected to an arc that actually turns out to be orthogonal to the boundary. And this is exactly how you get from one picture to the other. And now I want to give you, well, several animations of that process. So first of all, here's my version of that picture, and so that you see that all things are dynamically related, let me first move this point here. So you see three things. This here is the Beltrami Klein model, this here is the Poincare model, and this here is a three-dimensional picture that I just described. So you have two types of projections involved in that picture. So you have one orthogonal projection down in that direction directly from the North Pole that relates the unit circle of the Beltrami Klein model to the equator of your unit sphere. And then you have a stereographic projection going from the North Pole to this bigger circle here. And so one important thing, so this bigger circle here should at the end be our image of the Poincare disk, but you see it doesn't have the same size as the Beltrami Klein disk. It's actually scaled up by this construction by a factor of 2. So what you get down here in that image is the Poincare disk blown up by a factor of 2 that we have to keep in mind for everything that comes. So now we want to see what happens to a line under those projections. And I said, well, the first projection that we have to care about is orthogonal projection, and if you do that, you get, if you project this up to the sphere and only consider what happens in the lower hemisphere, you get a circular arc here. So first of all, why is this a circular arc? Well, essentially it's the intersection of a plane. So the orthogonal projection of that line to the sphere is cutting the sphere with a plane, and if you cut an arbitrary sphere with a plane, you get a circular arc. First observation. Second observation is if this is a circular arc and it comes from a plane that intersects orthogonally, then you will get a right angle here at that point. So the circular arc will be orthogonal to the equator at the boundary. So next thing, we take our stereographic projection, which means we take our north pole in our image and project this circular arc down to the plane. So again, keep in mind this is really a nice circle, and stereographic projections have the property that they send circles on the sphere to circles in the plane, though this arc down here will again be a circular arc as we want to have it in our Poincare model. Even more, circular arcs that you get here are again orthogonal to the equator, because stereographic projections preserve angles between circles. And I just told you that you have a right angle at that point here between the arc and the equator, and this right angle between the arc and the equator has to translate in a right angle between the two projected circles, which means our circular arc and the image of the equator under the stereographic projection, which is nothing else as our horizon of the Poincare disk. So essentially we understood everything now, and if you look at those images, you will see that if you focus on these two models, then you really get a relation of the Beltrami Klein image to the Poincare disk, blown up by a factor of 2. And as a matter of fact, if you draw these lines here through the center, then you will see, well, if you scale it down, then this arc here will really become the corresponding arc. Here you can do this scaling down also in our picture. We will do that in a moment. First I want to show you that this really works for arbitrary positions of our lines. So you see I can move around and this circle always stays orthogonal to the boundary. And so now we want to, well, do this scaling factor or undo this scaling factor, and we can do that by simply moving our intersection plane up to the equator. So I take my circle here and shift it to the equator, and then you have essentially sitting the Poincare disk of the correct size on top of the Beltrami Klein disk. And if you don't believe it, here you can see that they really match nicely if you view them from the top. Okay, now you have a vivid picture of Klein's model, and let me now draw a few consequences of what you get. Again, here this works for arbitrary positions, and if I sweep through that, you should, for instance, observe that if I sweep through the center, the circular arc in the Poincare model really becomes a line through the center of the circle, and we will need that fact in a moment. So let me show you a few animations where I place the Beltrami Klein model here and the Poincare model next to each other. So here we just have a line, and we already learned what happened. So this here will be a right angle to the boundary, and the 2 points here really are at the same positions of the horizon circle. So even if I sweep these things around, this relation remains constant. One important fact is, while things can get pretty narrow at the boundary of the Beltrami Klein model, in the Poincare disk you still have lots of space, plenty of space, because essentially the interior of that circle here gets squeezed by that factor of 2 that we just had, if you scale it down, and this space in the middle is sacrificed to have more space at the boundary, and this comes really as a very nice feature of the Poincare disk. So let me, as a second thing, do what I just said and move one of those points to the center of the circle. And what you see here, that in this case, those two models really agree with each other. So a line in the Beltrami Klein model will be just the corresponding line segment in the Poincare model. So if you have lines that pass through the center of the circle, then both models really represent them by the same line segment. And this in turn gives us a nice way to understand while angles in the Poincare model are such nice that they are really like the Euclidean angles between the circular arcs. So let's first focus on the situation where the two models agree. So assume you have two lines through the center of the hyperbolic disk, and you are interested what is the angle between these two lines. First of all, for this situation, both models are identical, and in an earlier lecture I proved that if you have lines through the center in the Beltrami Klein model, then this angle here that you get between the lines, the hyperbolic angle, is just the Euclidean angle you see here. So you can take your usual Euclidean angle measurement tool for this special situation where you really have two lines passing through the center and measure this angle, and this really is the hyperbolic angle. So it's also the hyperbolic angle in the Poincare disk. And if you now apply an arbitrary projective transformation to that image in the Poincare disk, so you make a CP1 projective transformation, then these lines here become circular arcs, and the midpoint gets mapped to any other point. And you can also think the other way around. If you have this picture here of two lines intersecting in some point, you can always find a corresponding projective transformation that sends them back to this situation. But projective transformations in CP1 don't change the angles between lines. So the angle that you measure here must really be the same that you measured here. So it is the angle between these circular arcs. So one calls this property conformality. So angles are not disturbed by this kind of representation. So in the Poincare disk, angles that appear to be a certain Euclidean angle are really the same angle also in hyperbolic geometry. Let me apply that to perpendicularity. Here again you see the Beltrami Klein versus the Poincare model, and here I've drawn two perpendicular lines, and you see they don't look perpendicular in the Beltrami Klein model, but they look perfectly perpendicular in the Poincare model. So you can start to move around, and so what you actually create in the Beltrami Klein model, you have all lines passing through that pole, and in the Poincare model you get all the arcs that are perpendicular to the red arc and the arc of the horizon circle. So let me again move around a little so that you see really this reflects the situation nicely. So even in extreme situation, when this angle here does no longer look like a right angle, you clearly see, well, it is a right angle because these two arcs here intersect in a right angle. So if we can talk about right angles, we can talk about triangle theorems, and here is the altitude theorem. So we proved that the altitude theorem holds for arbitrary Cayley-Klein geometries, and so it has to hold in hyperbolic geometry, which means that if I draw the three altitudes of a triangle, they will eventually meet in a point, and this will naturally also happen in the Poincare model, and this is nicely stable under movement. So essentially here we have proved a nice and strange theorem about circles in the plane, because everything we're doing here is essentially circles in the plane. Let me show you some interesting peculiarity that you get here. Let me move to a kind of more extreme position. So I move those points a little bit closer to the boundary, and now I move 1 point closer to the other two, and you see it may happen that the altitudes intersect outside the triangle. And well, this may happen even in Euclidean geometry, so this is not very special. But look what happens now. I move that point even a bit closer, and what you see, the altitudes no longer intersect. Or do they? Well, in a sense, if you look in the Poincare model, they still intersect outside our picture. So if I restrict myself to the universe inside this hyperbolic plane, then it may happen that the altitudes are lines that don't intersect in my finite world. And now let me become a little bit philosophical. Our starting point of the entire cycle of projective geometry was that we can get a way nicer theory than usual Euclidean theory if we extend our plane by a line at infinity. So we as beings in, say, presumably Euclidean geometry, we see, well, mathematically it is nicer to postulate there are points at infinity, and that the theory becomes way cleaner, free of special cases, any two lines intersect, any 2 points have a join, and so on and so on. Now assume for a moment that we are a being in hyperbolic geometry, and we are observing something like the altitudes of a triangle no longer intersecting. We may come to the conclusion that, well, there is a really cool system. Let's call it, well, the projective extension of our hyperbolic universe, where these lines still intersect in a point. Let's call that point hyper-infinite, because it's even further away than infinity. So my infinity here is this boundary, and this point here is even further away than going infinitely far away. And then as a being in hyperbolic space, I might reconstruct the same idea of a projective plane underlying everything that makes things way simpler. So you see, even if we were trapped in such a space, it would still lead to a projective view of our universe as a kind of nicer mathematical treatment. And then in that world we would discover what we would call a non-hyperbolic geometry, which may be the Euclidean geometry, and perhaps in that world it would take several thousand years to arrive at this other type of geometry. Okay, as a next thing, let me talk about circles. Most remarkable thing about circles is that in the Poincare model, circles really look like circles. So you here see a circle defined by a center and one of the perimeter points, and while in the Beltrami Klein model it becomes a squeezed conic, in the Poincare model, this circle really still is circular. This is a consequence of the special nature of having embedded this in the CP1 world and having the conformality here. So notice in Poincare disk, circles still will look like circles, but observe midpoints won't necessarily look like midpoints of that circle. Let me still move around a little. And next thing you may observe that if you make your circle really big, it becomes a circle that more and more approaches your horizon circle. So now let's do a next experiment. Let's take that point here and now take the center of the circle and move it to the boundary. And here I accidentally overshot a little, but it's very close to the boundary. And what you see, what you get is circles that are tangent to the horizon circle. And now again, imagine you are a being living in that world. It's no longer possible in that case to walk around and around and around, because if you walk here along that circle, you will never reach the boundary, because this is infinitely far away. So you can only pass through this circle from one point to the other in infinitely many steps, but you cannot go through that point. Now something really exciting happens. Let's take this point, this midpoint of the circle, and move it even further out. And when I first saw that after I did my implementations, I really was surprised, because what you get in the Poincare model is the following picture. You get two circular arcs intersecting at the boundary at a noticeable angle here. So the arcs here really seem to intersect in a certain angle. And if you look at the corresponding picture here, the picture still is a nice conic that just touches the boundary in 2 points. Let's again assume that we are a being walking in that world. So assume this time you've perhaps taken your bicycle. So this is me on my bicycle here. So a very bad drawing. This should be a bicycle. And I'm traveling in that direction. I took a bicycle because if you take the handle of your bicycle and move it to a certain position, then you will go in a circle. So you take your bicycle, put the handle in a certain position, and if this angle is small enough, the following may happen. You may go on and on and on and on and cycle on that path, and you will never reach that point. So actually, by walking in your bicycle trail, you can only walk on this circular arc. You will never be able to enter the other part here. So I will give you a 3D explanation of what's going on here in a minute. Then you will understand why this picture happens. Let me just move to a few other extreme positions. So you see, if the circle midpoint is outside, then it's really kind of two arcs intersecting in the boundary. I will explain it in a minute. Before I do that, I want to show you one more picture of walking in unit steps. So here I have in the Beltrami Klein model circles of all the same size, and so you see, they get more and more squeezed towards the boundary. And here I have the corresponding circles in the Poincare picture, and what you observe here is that you have way more space in that picture. Here, if you count the circles, you only get up to 6 or 7, and in the other pictures you can count on for a way longer time. So visibly the situation around the boundary here is really relaxed compared to the other model. So let me come back to this picture here of the two circular arcs, and let me explain to you why this happens, and let me again go to the three-dimensional picture. So again, we have the Beltrami Klein model here, we have the Poincare model here, and we have the three-dimensional picture here. This time I used the entire sphere as a projection frame because we need it to understand what's really going on here. So you have the Beltrami Klein model sitting in here as a unit circle, and the blown up Poincare model by a factor of 2 sitting outside. And this time you should observe why these Beltrami Klein circles appear so squeezed, because they are what you get if you project by your orthogonal projection a circle on the unit sphere down to the Beltrami Klein model. So let me move these things around a little, and I hope you get the impression that you really have circular cuts on the sphere. And actually you will not have only one circular cut, you will have two of them, because your circle here may intersect in the lower hemisphere and in the upper hemisphere. And if you stereographically project this circle down to the sphere again, you get a circle, and this is the reason why circles really appear to be circles in the Poincare model. So if you look at it from the lower side, you really see the squeezed Beltrami Klein circle here and the straight circle in the Poincare model here. So let me again move things around a little so that you get an impression. These here are really circles. So for a split second we had the orthogonal view to that circle, and so these are really intersections of planes with the unit sphere here. And as I said, you get two of them. If you get two of them, the other one here must have a projective image as well. And let's project the other circle as well. And what you get is a second circle that you don't see inside your horizon because it simply lies outside your horizon. So now let's focus on this second circle here that we have, and so I will turn off these projection rays because they will mess up my entire drawing. But you see the second circle here comes from projection of this other image of the circle. Now let me first move to the situation where you really have the center of the circle sitting at the boundary, and what happens here is that these two circles here will really just meet at the equator of our sphere, and you will just not see the second circle inside your horizon. But now if I move a little bit faster, these two circles here start to overlap, and you get an image of the second circle inside your disk here. So what you actually see, if you see those two circular arcs, you see images inside your Poincare model coming from the two representations of your circle. And you see, even if I move things around, it stays pretty stable. And if you look at it from the lower side and consider what you see in the planes, what you really will get is inside your horizon, you will get those two circular arcs. So I think now you have a better understanding why you see these two circular arcs in the general picture, and why the Beltrami Klein circles are squeezed in the way they are squeezed. And you even understand why the Beltrami Klein pictures really just touch the horizon circle in 2 points, because this is exactly what you get from that construction. Okay, this concludes our second part about the Poincare disk. In our final lecture of the projective geometry class that's coming next, I will, final interesting point, talk a little bit about triangles in hyperbolic geometry and how you can get really nice and impressive geometric patterns that really have a relation to art from these kind of triangles in hyperbolic space. We will see that in the next lecture. See you there.